Right now, above our heads, the sun is approaching a moment of intense transformation, a peak of activity it hasn't reached in over a decade. Ancient civilizations watched its every move with awe and fear. Today, with satellites and telescopes, we can finally see what they could only imagine. But here's the question: have we already reached the sun's maximum, or is the real storm still ahead? Chapter 1: The living heart of our solar system. If you step outside on a clear day and look up, you see the sun as a steady, glowing disk. It feels unchanging, the same star our ancestors saw thousands of years ago. But the truth is, the sun is not still. It is alive, in its own way. It pulses, it shifts, it erupts. It is the beating heart of our solar system. For as long as humans have looked at the sky, the sun has been more than a source of light. It was a god to some, a clock to others, and a mystery to all. The ancient Egyptians saw it as Ra, the god who sailed his golden boat across the heavens each day. In Inca culture, it was Inti, the divine father of their people. Even in places far from deserts or mountains, the sun became a symbol of power, life, and rebirth. Civilizations aligned temples to track its movement, marked calendars by its rise and fall, and built myths around its journey. But the sun we know today is not just the sun of myth. Modern science has stripped away the divine disguise and revealed a star, a massive sphere of plasma held together by gravity, powered by nuclear fusion deep in its core. Every second it turns hydrogen into helium, releasing an unimaginable amount of energy. That energy is what warms our planet, drives our weather, and makes life possible. Without it, Earth would be a frozen rock drifting in darkness. Still, knowing the sun is just a star doesn't make it less incredible. In fact, it makes it more fascinating. It's not a static object. The sun changes every moment, in ways both subtle and violent. Its surface boils with storms the size of Earth. Its magnetic fields twist and snap, hurling matter into space. Invisible waves of charged particles stream outward in all directions, shaping a bubble around our solar system known as the heliosphere. The sun's activity isn't random. Over time, scientists have discovered it follows patterns, cycles of high and low activity that repeat every 11 years or so. These are called solar cycles. During a solar maximum, the sun is restless, with more sunspots, more flares, and more eruptions. During a solar minimum, it appears calmer, with fewer visible signs of turmoil. To people in the past, these patterns were invisible. They could see sunspots through simple telescopes, but they didn't know the full story. It wasn't here until the early 20th century that astronomers began to connect these changes to a repeating cycle. And only in recent decades, with the help of space telescopes and satellites, have we been able to see the sun in detail across the spectrum. From the blinding light our eyes can see, to the hidden energy of ultraviolet and X-rays, this ability to watch the sun in different wavelengths has transformed our understanding. In visible light, we see the familiar golden disk. In ultraviolet, we see the churning loops of plasma arching high above the surface. In X-rays, we see the raw power of solar flares as they release bursts of energy into space. Each wavelength reveals a different layer of the sun's personality, and the more we watch, the more we realize the sun's story is one of constant change. It is not a background object in the sky. It is an active player in the life of Earth. Its magnetic storms can trigger auroras, but they can also disrupt satellites, communications, and even power grids. Its brightness changes subtly over time, influencing our climate in ways we're still working to understand. Think about this. Every moment, the sun is shaping our environment without us even noticing. The warmth you feel on your face, the gentle push of wind over the ocean, the balance of seasons, all of it is tied to the sun's energy. And yet, for most of human history, we have treated it as a constant, something that simply is. Now we know better. What makes this even more intriguing is that the sun's changes aren't isolated to the sun itself. Its activity sends ripples across the solar system. The solar wind, a stream of charged particles flowing outward, interacts with planetary atmospheres, carves out comet tails, and shapes the magnetic boundaries of planets like Earth, Jupiter, and Saturn. In a way, the sun is like a conductor, and every planet is an instrument responding to its rhythm. Our ancestors might not have had the science to explain it, but they sensed something powerful in the sun. They built monuments to mark solstices, times when the sun reached its highest or lowest point in the sky. They celebrated harvests when the sun's warmth returned in spring, and they feared the long nights of winter when it seemed to fade. The sun's rhythm was woven into their lives, just as it is woven into ours. Today, we stand in a unique position. We still feel that ancient awe when we watch a sunrise or see the first rays break through the clouds. But we also have the tools to measure the sun's heartbeat. We can count sunspots, track its magnetic fields, and detect the energy it sends our way. We can even predict some of its moods, not perfectly, but enough to prepare for the storms that might affect us. And now, in the year 2025, we find ourselves at a critical moment. The sun is deep into its current cycle, solar cycle 25. Sunspot numbers are climbing. Solar flares are becoming more frequent. Auroras have been appearing at lower latitudes than usual. The question on every solar scientist's mind is the same. Are we at the peak, or is the true maximum still ahead? The answer isn't simple. The sun has a way of surprising us. Sometimes it peaks earlier than expected. Sometimes it surges late. And sometimes it gives us false signals, bursts of activity followed by unexpected lulls. Predicting its behavior is like predicting the mood of an ocean. You can see the waves, but you don't always know what's coming next. In the chapters ahead, we'll look closer at this cycle, at the data scientists are collecting, and at what it means for Earth. We'll explore the risks, the beauty, and the long history of our relationship with this star. But before we move forward, remember this. The sun you see today is not the same sun you saw yesterday. It has changed, it will keep changing, and its story is far from over. Chapter 2. Understanding the solar cycle. If you've ever noticed that the sun looks the same from one day to the next, it's easy to assume it's unchanging. But beneath that steady glow is a rhythm, a long, slow pulse that repeats over and over. This is the solar cycle. And understanding it is like learning the sun's natural heartbeat. At its simplest, the solar cycle is about the sun's magnetic field. Imagine the sun as a giant bar magnet with a north and south pole. Over time, that magnetic field slowly twists and flips. About every 11 years, the sun's poles swap places. North becomes south, and south becomes north. This flip is more than just a curiosity. It's what drives the rise and fall of solar activity. We see this change most clearly through sunspots. These are darker areas on the sun's surface where magnetic fields are especially strong. They might look small in telescope images, but many are larger than Earth itself. Sunspots are cooler than their surroundings, which is why they appear dark, but they're also centers of intense energy. The more sunspots we see, the more active the sun is. In a solar minimum, sunspots are rare. The sun's face might be completely blank for weeks or months. Flares and eruptions are less frequent. It's the sun's quiet phase, though quiet is a relative term, even in minimum. The sun is still powerful beyond anything on Earth. As the cycle moves toward a solar maximum, the sun's magnetic fields grow more tangled and unstable. This leads to more sunspots, more flares, and more coronal mass ejections. Massive bursts of plasma that can travel millions of miles an hour. These events are spectacular to watch through space telescopes, but they can also have real effects here on Earth. Scientists have been tracking these cycles for centuries. The first recorded observation of sunspots through a telescope came in the early 1600s, by astronomers like Galileo in Italy and Thomas Harriot in England. Over time, patterns began to emerge. In the mid-1800s, the German astronomer Samuel Heinrich Schwab noticed that sunspot numbers seemed to rise and fall in a regular rhythm. His work became the foundation for our understanding of the 11-year cycle. Since then, we've recorded over 24 cycles. Some have been strong, with intense maxima that produced bright auroras, visible far from the poles. Others have been weak, with fewer storms and lower overall activity. One of the most famous weak periods was the Maunder minimum in the 1600s, when sunspots almost disappeared for decades. This coincided with a colder climate in parts of the world, sometimes called the Little Ice Age, though the link is still debated. So why does this cycle matter? Because the sun's activity affects more than just the space above our heads. Strong solar storms can disrupt satellites, interfere with GPS, and cause radio blackouts. In rare cases, they can overload power grids, leading to blackouts on Earth. The most famous example is the 1989 Quebec blackout, when a geomagnetic storm knocked out power to millions of people in Canada. But there's another side to the story, the beautiful one. Increased solar activity means more chances to see the aurora borealis and aurora australis, the shimmering lights in the night sky. During a strong maximum, these lights can be seen much farther from the poles than usual. In past cycles, people in southern Europe, the southern United States, and even the Caribbean have seen auroras. To study the cycle today, scientists use more than just ground-based telescopes. We have spacecraft like NASA's Solar Dynamics Observatory, the European Space Agency's Solar Orbiter, and the Parker Solar Probe, which is flying closer to the Sun than any spacecraft in history. These missions give us high-resolution images, magnetic field maps, and real-time data on solar wind and particle streams. By tracking sunspot counts, measuring magnetic field strength, and watching for flares, scientists can estimate where we are in the cycle. They can even make forecasts, though predicting the Sun is never exact. Sometimes a cycle is stronger or weaker than expected. Sometimes it peaks earlier or later. That uncertainty is part of what makes studying the Sun exciting. Every cycle has its own personality. Some are short, lasting only about 9 years. Others stretch closer to 14. Some have sharp high peaks of activity. Others have broad, flat maxima. Scientists are still working to understand why these differences happen. They believe it's tied to the Sun's internal dynamics, the movement of plasma inside its layers. But the details remain mysterious. Another thing to know is that the Sun's influence extends far beyond Earth. Its magnetic field and solar wind create a bubble around the entire solar system, called the heliosphere. During solar maximum, the stronger solar wind pushes this boundary farther out. During minimum, it contracts. This means the solar cycle affects the space environment for every planet, moon, and spacecraft in the solar system. There's also a deeper connection to Earth's climate. While the Sun's energy output only changes slightly over a cycle, those small changes can influence weather patterns in complex ways. Scientists are cautious about linking short-term solar changes to climate trends, but they do study these effects as part of the bigger picture of how Earth's environment responds to the Sun. From a human perspective, the solar cycle is both a scientific puzzle and a reminder of our place in the cosmos. We live inside the influence of a star. Its moods shape our technology, our skies, and even our sense of wonder. Understanding the cycle helps us prepare for the challenges it can bring and appreciate the beauty it creates. Right now, we're in the middle of Solar Cycle 25, which began in late 2019. The last few years have shown a steady climb in activity, with sunspot numbers exceeding early predictions. That's why scientists are paying close attention. Some believe we may be approaching the maximum already. Others think the strongest storms are still to come. In the next chapter, we'll focus on Solar Cycle 25 itself, where we stand, what's already happened, and what we might expect in the months ahead. The Sun is speaking in its own language of flares, spots, and storms. Our job is to listen. Chapter 3. The State of Solar Cycle 25. When Solar Cycle 25 officially began in December 2019, scientists thought it might be a modest one. Early forecasts suggested it would be similar in strength to Cycle 24, which was considered relatively weak. Many expected a slow climb toward the peak, with moderate solar storms and limited disruption to technology. But the Sun had other plans. By late 2021, sunspot numbers began to rise faster than expected. The official predictions had to be adjusted upward. What was supposed to be a calm cycle started showing signs of more intense activity. And in the world of space weather, surprises like this matter. One of the first hints came from a sudden jump in sunspot counts. Instead of a steady, predictable curve, the numbers shot upward, breaking past the forecast range. At the same time, solar flares became more frequent. We started seeing M-class flares, medium-strength bursts of energy on a regular basis, and even the occasional X-class flare. the most powerful kind. Why is this important? Because solar flares release massive amounts of electromagnetic radiation. When aimed at Earth, they can cause shortwave radio blackouts, especially in the polar regions. Pilots flying high-latitude routes, such as between North America and Asia, sometimes have to change course during strong events. Cycle 25 also brought a surge in coronal mass ejections, or CMEs. These are huge bubbles of plasma launched from the Sun's outer atmosphere. When ACME hits Earth, it can compress our planet's magnetic field and trigger geomagnetic storms. These storms can create spectacular auroras, but they can also put stress on satellites and power grids. One of the most dramatic events so far happened in February 2022, when a geomagnetic storm caused 40 newly launched SpaceX Starlink satellites to fall back into Earth's atmosphere. The increased drag from the storm's effects in the upper atmosphere made it impossible for the satellites to maintain their orbits. It was a costly reminder that space weather isn't just an abstract concept. It can have immediate, real-world consequences. By 2023, it was clear that solar cycle 25 was not just keeping pace with predictions, it was outperforming them. Monthly sunspot counts were regularly exceeding what the experts had forecast. NASA and NOAA revised their outlooks, now suggesting the maximum could be stronger and arrive earlier than originally thought. Instead of peaking around 2025, there's a chance it could happen as early as 2024. For those living at higher latitudes, this has been good news for aurora watching. Photographers in places like Canada, Alaska, and Scandinavia have enjoyed multiple nights of bright, colorful displays. Even parts of the United States and Europe that rarely see auroras have been treated to the lights. Social media has been filled with images of pink, purple, and green ribbons stretching across the sky, a visual gift from our active sun. But increased activity also means heightened risk for technology. Modern society depends heavily on satellites for communication, navigation, and weather forecasting. Strong geomagnetic storms can degrade or even disable these systems. Airlines, shipping companies, and emergency services all rely on GPS. The more active the sun becomes, the more these sectors need to prepare. Monitoring solar cycle 25 is a daily task for space weather centers around the world. In the United States, NOAA's Space Weather Prediction Center issues alerts and warnings, much like a weather bureau would for a hurricane. Observatories in Europe, Asia, and South America also contribute data, creating a global network of watchers. What makes Cycle 25 particularly interesting is how it's being observed. Unlike in past cycles, we now have the Parker Solar Probe and the Solar Orbiter gathering data from inside the Sun's outer atmosphere. Parker has been diving closer and closer to the Sun, flying through regions of the solar wind we've never directly sampled before. Solar Orbiter, meanwhile, is giving us high-resolution images of the Sun's poles, a region we know surprisingly little about. This new data could help explain why Cycle 25 is behaving the way it is. Are we seeing a shift in the Sun's long-term patterns? Is this just natural variation, or a sign of something bigger? Scientists don't have a definitive answer yet, but each flare, storm, and sunspot adds a new piece to the puzzle. Another fascinating aspect is the link between solar cycles and cosmic rays, high-energy particles from outside our solar system. During solar maximum, the Sun's magnetic field is stronger, which helps shield Earth from some of these particles. During solar minimum, the shielding is weaker, and cosmic ray levels rise. That means the timing and strength of solar cycle 25 will affect not just space weather, but also the radiation environment for astronauts and spacecraft. Right now, as we move deeper into the active phase, the Sun is showing a mix of behaviors: clusters of sunspots across its surface, frequent C and M-class flares, and a steady stream of CMEs. While none of the storms so far have been as severe as the legendary Carrington event of 1859, which lit up skies around the world and disrupted telegraph lines, the potential for a major storm always exists. For everyday people, most effects are invisible unless you're looking for them. Your phone still works, your lights stay on, and life continues as normal. But for scientists, engineers, and those who work with space-based technology, the sun's mood is always on their radar. In the months ahead, experts expect the activity to stay high. We may see more X-class flares, stronger geomagnetic storms, and more widespread auroras. It's a time of both opportunity and caution, a chance to witness the sun's power, while also respecting its ability to disrupt. In the next chapter, we'll explore how these changes in the sun affect life on Earth, from the science of auroras to the risks of space weather for our technology and infrastructure. The story of Solar Cycle 25 isn't just happening in space, it's unfolding right here, under our own sky. Chapter 4. How solar changes affect Earth. When the sun's activity changes, it doesn't just stay up there in space. Its effects ripple through the solar system and reach all the way to our daily lives here on Earth, sometimes in ways we can see, and other times in ways we don't notice until something stops working. One of the most beautiful and visible effects is the aurora, the shimmering curtains of light that dance in the sky near the poles. These lights appear when charged particles from the sun collide with gases in Earth's upper atmosphere. Oxygen produces green and red light, while nitrogen gives shades of blue and purple. The stronger the solar storm, the farther from the poles the auroras can be seen. During particularly active periods in Solar Cycle 25, people in places like New York, Scotland, and Germany, locations that normally don't see auroras, have been able to witness them. For photographers and skywatchers, this is an exciting gift from nature. But auroras are just the visible tip of the iceberg. Behind the beauty lies something more powerful: geomagnetic storms. These storms happen when a coronal mass ejection (CME) or a high-speed solar wind stream hits Earth's magnetic field. The collision causes the field to ripple and shift, creating electric currents both in space and on the ground. On the ground, these currents can flow through long power lines and pipelines. In extreme cases, they can damage transformers and cause blackouts. The most famous example was the 1989 Quebec blackout, when a geomagnetic storm took down the power grid for millions of people for about 9 hours. Engineers had no choice but to shut down the system until the storm passed. Satellites in orbit are also vulnerable. A sudden burst of solar energy can heat and expand the upper atmosphere, increasing drag on satellites in low Earth orbit. This is exactly what happened to SpaceX's Starlink satellites in early 2022. The satellites couldn't recover and re-entered the atmosphere, burning up before they could reach their planned positions. Other times, high-energy particles from solar storms can damage the sensitive electronics inside satellites. A glitch in a weather satellite or GPS network can cause widespread disruption for navigation, shipping, and even military operations. That's why space agencies around the world monitor the sun 24/7. It's not just for science, but for safety and reliability. A less visible but still serious effect is radio communication disruption. Shortwave radio, used by ships, aircraft, and remote communities, can be knocked out for hours during strong solar flares. The most intense flares, called X-class, can cause complete radio blackouts on the sunlit side of the planet. For airlines flying over the Arctic, this can mean changing routes mid-flight, costing extra fuel and time. Radiation exposure is another concern, especially for astronauts. During big solar storms, the level of energetic particles in space can rise dramatically. Astronauts aboard the International Space Station are shielded by Earth's magnetic field, but those traveling farther, like to the Moon or Mars, would be more exposed. That's why future space missions must plan around solar activity, using forecasts to avoid dangerous radiation events. There's also the link between the sun and climate. Though it's complex, solar cycles do affect the amount of energy Earth receives, but the variation is small compared to human-caused climate change. However, some researchers are studying how long-term patterns in solar activity may influence things like atmospheric circulation or regional weather patterns. It's an area of science still filled with questions. For the average person, the most direct impact of an active sun might be in navigation and communication. GPS signals, which bounce between satellites and receivers on Earth, can be distorted by solar activity. This might make your phone's location services less accurate. or cause delays in systems that depend on precise timing. From bank transactions to emergency services, the good news is that we're better prepared now than in the past. Power companies can take protective measures when a storm is coming. Satellite operators can switch spacecraft into safe mode to avoid damage. Airlines can reroute flights ahead of time. All of this depends on space weather forecasting, an area of science that has improved greatly but still faces challenges. The most important thing to remember is that the sun is not our enemy. Its activity is part of a natural cycle that has been happening for billions of years. Without it, there would be no life here. The challenge for us is to understand its moods, anticipate its bursts of energy, and adapt when it decides to put on a show. Whether that's a gentle aurora or a storm strong enough to shake our technology. As solar cycle 25 continues, we're likely to see more examples of both beauty and disruption. Some of them will make headlines. Others will pass unnoticed except by scientists and engineers, but all of them are reminders that we live in a system powered by a star that is alive with movement, heat, and magnetic energy. In our final chapter, we'll look ahead, exploring what these changes could mean for the future, what scientists hope to discover, and how our relationship with the sun might evolve as technology and exploration take us further into space. Chapter 5. The future of our sun. When we talk about the future of the sun, we are really talking about the future of everything in our solar system, including us. The sun is the clock that keeps time for life on Earth. It has been burning for 4.6 billion years, and it will continue for billions more, but it will not stay the same. Like all stars, the sun is evolving. Right now, it's in what astronomers call the main sequence stage, a long, stable period where it converts hydrogen into helium through nuclear fusion in its core. This process releases the light and heat that make life possible here. But in about 5 billion years, the sun will run out of hydrogen fuel in its core. When that happens, it will change dramatically. The core will contract, heating up, while the outer layers expand. The sun will grow into a red giant, swelling so much that it may engulf Mercury, Venus, and possibly Earth. If Earth survives physically, its surface will be scorched beyond recognition. This is far, far in the future. Long before then, human civilization will have changed, or moved, or perhaps found ways to adapt. But the idea that our sun has a life cycle just like living things on Earth is a powerful reminder. Nothing in the universe is truly permanent. Before that distant red giant stage, the sun will keep going through its 11-year solar cycles. Solar cycle 25, which we're in now, will peak around 2025 to 2026. Scientists are already watching for stronger flares, more coronal mass ejections, and larger sunspot groups. These cycles are windows into the sun's magnetic heart. In the near future, solar science is entering a golden age. The Parker Solar Probe, launched by NASA, is flying closer to the sun than any spacecraft before it. It's literally diving into the outer atmosphere, or corona, to study the origins of solar wind and the mysterious heating process that makes the corona hotter than the surface. Meanwhile, the Solar Orbiter, a European Space Agency mission, is taking high-resolution images of the sun's poles, an area we've never seen clearly before. These polar regions hold clues about how the solar magnetic field flips every cycle, a process that drives solar activity. Better understanding means better forecasting. One of the big goals is to predict solar storms with the same accuracy that we predict hurricanes. If we can give power companies, airlines, and satellite operators days or even hours of warning, we can prevent most of the damage that solar storms cause today. The future also includes something more philosophical, how we think about the sun in human culture. For ancient civilizations, the sun was a god. Ra in Egypt, Helios in Greece, Amaterasu in Japan. These myths were born out of awe and dependence. In our modern age, the sun is still a source of wonder, but now we can explain its behavior with physics instead of myth. Yet the emotional connection remains. We've also begun to use the sun in new ways. Solar energy technology is improving every year. Massive solar farms and even small rooftop panels are capturing the sun's power directly to run our homes, cities, and industries. If we can store and distribute that energy efficiently, it could replace much of our dependence on fossil fuels. There are even futuristic ideas, like building giant solar collectors in space to beam clean energy back to Earth, or using sunlight to power spacecraft for deep space exploration. The Japanese Icarus probe has already tested a solar sail, riding photons like a ship rides the wind. On a much longer timescale, if humanity survives far into the future, we may need to leave Earth before the sun's changes make it uninhabitable. That could mean building space habitats, colonizing other planets, or even traveling to other star systems. The sun's life story is tied to ours, but it does not define our limits. Thinking about the sun's future also means thinking about how much we still don't know. Why is the solar corona so hot? How exactly do sunspot cycles affect Earth's climate? Could there be rare superflares on stars like our sun? And if so, how dangerous would they be? These are the mysteries that will guide space research for decades. The more we study the sun, the more we see it as both a scientific puzzle and a source of inspiration. It is the reason we exist, the ultimate provider of energy. And yet, it is also a powerful force that can disrupt our lives in an instant. Balancing respect, curiosity, and preparation is the key to living with our star. As we look ahead, one thing is certain: the sun will keep changing, and so will our understanding of it. Every new observation, every mission, every theory brings us closer to seeing the full picture. And with that knowledge comes a deeper appreciation, not just for the sun itself, but for our fragile place in the cosmic story. If you've enjoyed this journey into the sun's past, present, and future, let's keep exploring together. Hit the like button to let more people see this story. Subscribe for more deep dives into the science of space, and share your thoughts in the comments. What fascinates you most about our sun? The conversation is as endless as the light it gives us.